To make general relativity and the Standard Model function at extreme scales, physicists routinely patch the math with unobserved phenomena. The Standard Model is the theoretical framework classifying all known elementary particles and three of the fundamental forces. Entities like dark matter halos, the inflaton field, and dark energy are treated as tunable parameters. When an observation diverges from the mathematical prediction, theorists adjust these parameters to bridge the gap. Physicist Satish B. Thorway approaches the problem differently. His dynamic vacuum field theory, or DVFT, posits that the vacuum is a physical, complex scalar field rather than an empty void. The theory is anchored by this single equation. The field has two distinct components, amplitude, represented by rho, and phase, represented by theta. Deriving its physics strictly from this interplay using fixed parameters, it operates as a zero-tuning framework. These constants cannot be adjusted. This rigidity makes the theory highly falsifiable. A single predictive mismatch across any scale of physics completely breaks the framework. This diagram visualizes the structure of Thorway's vacuum. It acts as a dual-layered dynamic environment. The bottom layer is the amplitude, or rho. This component encodes inertial and gravitational density, and it possesses a specific fixed vacuum density. The top layer is the phase, or theta. This vector field governs quantum coherence, the fundamental forces, and the dynamics of time. The theory establishes a fixed intrinsic stiffness for this vacuum environment, designated mathematically as K0. This dynamically forming equation demonstrates the theory's structural logic. The speed of light is not an arbitrary constant here. It is strictly derived from the square root of the vacuum stiffness divided by the vacuum density. Because these specific parameters are inextricably locked and successfully derive established physical constants, the theory asserts they must resolve observational anomalies on their own without requiring secondary adjustments. We can test this first at the quantum scale, where local environments alter the vacuum's amplitude. Particle physics currently faces an anomaly regarding neutron beta decay. There is a persistent 9-second discrepancy in measured lifespans depending on the testing method, specifically between open neutron beams and enclosed magnetic bottle traps. This graph maps the mathematical energy barrier for decay. DVFT calculates that the physical trap walls, or electromagnetic fields in a bottle trap, induce a microscopic shift in the local vacuum density, visibly lowering that decay barrier. That precise density shift mathematically calculates to roughly a 1% shortening of the neutron's lifetime. This perfectly matches the observed 9-second anomaly. The Standard Model predicts identical lifetimes regardless of the physical trap used. If upcoming high-precision experiments at the National Institute of Standards and Technology show no geometric variation, DVFT fails entirely. A second quantum prediction places a hard limit on macroscopic quantum superpositions, based entirely on the energy limits of the vacuum's phase field. When the gravitational distortion of an object exceeds the field's phase stiffness, the energy cost forces the superposition to physically collapse. DVFT connects macroscopic gravity directly to quantum decoherence. This yields a testable cutoff limit of roughly 10 to the 8th atomic mass units, a hard boundary that standard quantum mechanics currently lacks. An atomic mass unit is a standard metric that quantifies mass on an atomic scale. Moving from the quantum to the galactic scale allows us to test these exact same fixed parameters against rotational anomalies. This is a photograph of the Andromeda galaxy. Standard astrophysics assumes that a massive, invisible halo of dark matter is required to keep its outer stars from flying apart as the galaxy rotates. This graph plots the orbital speeds of visible stars across a galaxy. DVFT's deep field nonlinear vacuum response natively calculates a flat galactic rotation curve, precisely matching observed velocity using strictly baryonic, or normal, mass. Applying this exact calculation to Andromeda yields an orbital velocity of 220 kilometers per second, completely matching observational data. The ultimate historical evidence for dark matter relies on the bullet cluster collision, highlighting the hot gas in pink and the gravitational mass in blue. Standard models require a massive cluster of collisionless dark matter particles to explain the 250 kiloparsec offset between the lensing mass and the visible gas. A kiloparsec is a unit of astronomical distance equal to about 3,260 light-years. DVFT offers a purely baryonic explanation. As two clusters merge, the colliding baryonic gas swirls in the center, while vacuum stress energy perturbations, specifically ripples in the phase field, decouple and pass entirely through the collision zone. These decoupled phase waves mathematically reproduce the exact effective lensing signature measured at the outer edges of the cluster, 2 × 10⁻14 solar masses. What astrophysics has interpreted for decades as a halo of invisible particles is, under DVFT, the observable stress energy signature of the vacuum's phase field decoupling from physical mass. Expanding to the universal scale, we can apply the theory to the deepest current anomaly in cosmology, the Hubble tension. The Hubble tension is the unresolvable discrepancy between the universe's expansion rate in its early stages, measured by the cosmic microwave background, and the structured late universe's expansion rate, measured by supernovae. The cosmic microwave background is the residual thermal radiation left over from the early stages of the universe. DVFT utilizes a mechanism known as vacuum backreaction to explain this precise discrepancy. This split-screen diagram maps the vacuum potential in 2 different epochs. On the left, the smooth, homogeneous nature of the early universe dictates a specific lower vacuum potential, yielding the precise expansion measurement of 67 kilometers per second per megaparsec. A megaparsec is equivalent to roughly 3.26 million light-years. As matter clumped into galaxies, local backreaction increased the vacuum potential. The warped and clustered field on the right side naturally outputs the local expansion rate of 73 kilometers per second per megaparsec. The standard cosmological model, lambda CDM, requires injecting unproven physics to explain this exact split. Lambda CDM is the current standard framework parameterized by dark energy and cold dark matter. Under DVFT, the Hubble tension is not an error in measurement. It is a direct, mathematically expected topographical feature of a dynamic vacuum field. DVFT provides a singular, mathematically locked scalar field capable of resolving neutron decay, galactic rotation, and the expansion rate of the universe simultaneously. Because the intrinsic parameters cannot be adjusted to accommodate new data, the entire framework is structurally brittle and relies heavily on upcoming precision tests. Upcoming early universe galaxy clustering data from space observatories like the James Webb Space Telescope will test the accelerated structure growth predicted by these exact vacuum fluctuations. Simultaneously, observatories like LIGO are searching for extra-scalar gravitational wave polarizations caused by phase waves, a strict deviation from pure general relativity. Future space missions will target the specific 10 to the 8th atomic mass unit superposition cutoff limit. If these upcoming tests require a single dark matter particle or a tuning adjustment outside the defined amplitude and phase dynamics, DVFT fails. If the data aligns, the dark sector is obsolete.